Then this is important in trying to find a second solution for this equation, right? And that's what we will do, right? And now let's get some space because we already have that. We already have all this. We just need to find a second solution. So assuming y sub 1 satisfies this one, y sub 1 is a solution. It's a known solution of this differential equation. Now we can use the fact that we know the solution of Arfken to try to solve for y sub 2, because when you write this out, this is y1 y2 pi minus y1 pi y2, right? And this is equals to w. Now we can substitute this into here, and that is given by this, whatever that solution, into the minus. It's basically it's a function of x. The right-hand side is a function of x. And then you have this differential equation. And you know how to solve? This is a differential equation for y2, right? You know how to solve this one? What is the form of this one? This we did that in one section, right? Oh. Right. That yeah, there's a formula for that. This one, because the form is what we classify it. It's first order, right? Because that's only involve one derivative, and it's linear. So first order linear differential equation, and we actually have a formula. I think I talk about that. The formula actually is useful for many purposes, and useful to derive other things. And one thing now we use is to solve for this equation, to get to this formula, right? And to use that formula, we put it in the standard form. So the standard form involves just y2 pi and minus, basically divide y1 to the other side. The y1 pi over y1 multiplied by y2 equals to whatever that is, y1. That is a function of x. This is also a function of x. Okay, now this is in the standard form. I think in the standard form we call that p. We got that is p, and this is q, right? But we already use p here, so it's a little confusing. But it's just using the same formula, right? Then, well, I think we could just try to write. If you remember the formula, to write down the solution right away. I think we did it somewhere. So e to the minus of that, because when you take a derivative, you want to cancel that. This is the minus, because I already have a minus sign, so your x. And another simplification is y1 pi divided by y1 is log y1 pi. Y1 pi is this x pi. And we can choose like what we did this. It doesn't have to be exactly 0. Just face any x sub 0, right? And the minus is, you already have a minus sign, right? So you take the derivative of that over here, then the derivative of this one will give you the exponential of this one, which is, the same exponential. And take the argument, take the derivative over the argument, give you log y pi in front of the same exponential. Log y pi is just y1 pi divided by y1. So that two we cancel. And then the rest is, I think, the standard form is, this is y2 0 at this x equals 0. And then plus the right-hand side, integrate over, I think it's the same x0, right? And the x prime, and then the, whatever that function, y1 x prime, exponential function now is this one is just copy that because this is just part of the what we call the Q in the formula. Q. Well, we already use pi, that's double pi. Right. So that is the Q that go into here, and then we get the exponential function. That is you want to get the x prime over x0 with the minus sign, log x, log y prime. X. Now this can be double prime. This is y sub 1. Y sub 1, y sub. Right. That's the solution. All right. Now we can simplify that because this is a total derivative, log y1 prime, and take a derivative. So this becomes log y1 and evaluate at the limit, right? Becomes log, right? Explicitly becomes log y1 at x divided by y1 at x of 0, right? So that becomes this one. See, because it's total derivative, right? So you just evaluate the argument of the function that you took the derivative and evaluate at the limit. So this upper limit minus the lower limit in the log, it becomes a log of the ratio. Is that okay? So that is this term, and then I mean, many of these are just constant. We'll later on just choose our own constant. But that doesn't matter. Keep this first. And this one is simplified, just like what we did over here. So it's minus log. Oh, you can write another exponential function. X prime over x of 0. Right? And now you just use the fact that exponential of log is just given you the argument. It just doesn't matter. And now we can choose your constant, this one, because our purpose is to find a linear independent solution. And then if you take the exponential function of that, that's proportional y1 divided by y1 at x sub 0, which is just a constant. And the first term is multiplied by another constant. So overall, the first term is just a constant multiplied by y sub 1, right? Which is the first solution you assume. And you want to find a solution that's linear independent of that. So adding a solution, original solution doesn't matter because that's make it dependent. Adding any constant time, the first solution is just not independent of the first solution. So you have a choice of this. You can choose your initial point to be 0. So initial y2. So to simplify the formula, adding this just doesn't give you anything new because you're just adding a constant times the original function, right? So you have a freedom to choose that to be 0, right? And now this is I write it too fast. Y1 as x prime, y1 as x0. Right. All right. Now let's just simplify that. Y1 at x divided by a constant, and it's another constant WA, and then x sub 0 to x pi, and you have this first exponential minus certain lower limit to x pi, p x double pi dx double pi. Right, and then this one, just the same argument, the exponential of the log, but then you have a negative sign, so basically flip the upper, I mean the numerator and denominator becomes you already originally have a y1 pi, y1 x pi already, and flip it, you have another y1 at the denominator, so you square. And you have another constant y1 x sub 0 over here, which cancels with this one. Right? Well, I forgot this integrating sign. This is dx pi. That's dx pi. Dx pi. Well, did I write wrong? Well, it's dx pi is integrating to x, not x pi. Integrating to x. That is x pi. Okay. Okay. All right, so that is close to our final form. It's just you have a proportionality constant W sub A, which is arbitrary, and you have this integration limit, which is also arbitrary, x sub 0 and A. So whatever you use, that doesn't give you new things, so you can choose this all three parameters. It's overall constant or this limit, because if you choose the other one, you just get another linearly dependent solution of y1. Right? So the overall formula is just, you can write, I think your textbook has this formula without writing the limit. This is 7.67. So either this one, so you use a textbook, 7.67 divided by 2x is overall is multiplied by y sub 1. This integrating over x to x, and just leave the lower limit as a parameter. And then you have the exponential function of minus integrating the x prime, which is the variable that we, I mean, your textbook you use the x sub 2, which you can follow that or just use our convention. Right. And then leave the lower limit as unspecified. And then y1 square of x pi dx pi. Okay. So this is the same as this one, without all these specified constant. Is it okay? So that's the formula that you can use, and which apply to this second order equation. Right. Obviously, you can generalize to high order solutions using the same method. It will become more complicated, but at least that's doable. It's okay. So that I think that's this section to derive this formula or know that this is the formula to use is the most important thing, because once you know the formula, that will help you to find a solution. But sometimes you have given a second order ODE, you can basically, sometimes you can guess one solution easily, but the other solution becomes more complicated. Once you see one solution, so choose that as y sub 1 and do this integral. You have y sub 1 in here and y sub 1 in the denominator, but you need to integrate that. And with this parameter, if p is 0, that becomes much easier. If p is 0, this is just 0, and this exponential function is just 1. That formula becomes easier. But if P is not 0, then you need to do this maybe complicated integration. Still, it's a straightforward formula. It's okay. So that's the derivation. Is okay? All this, how you get to this formula? I mean, basically, you just apply the formula without going through this. But this derivation is just another example for you to see that the formula that I gave you the last time, the linear first order ODE is important. Is you basically use that quite often in getting your new result, because it's that kind of the basic building block that you can use to do more complicated things. All right.